My name is Harrison Leary, and this is my Physics 2 Lab 4 on circuits. So for an introduction, the purpose of this lab is an investigation of the loop rule, which is essentially conservation of energy, the node rule, which is essentially conservation of charge, and the definition of the steady state in regards to circuits, which means that the current is constant and there's a non-zero E field inside the conducting wires. So as well with the physics principles, the potential difference of a capacitor plus the potential difference of a resistor will be equal to 0. Q over RC plus dQ over dt is also equal to 0, which will be used later along with the formula listed below with the natural log. This will be used in our graph. And then finally, that the change in potential difference is equal to current times resistance. So for the experiment itself, our system is the circuit including the battery, bulbs, capacitors, and wires, and our surroundings are the earth, table, and everything else, which are all negligible in this experiment. And both series and parallel circuits were constructed with our series and RC circuits. And some errors may include faulty materials, particularly the wires in my case. Some of them were quite frail, and poor connection between the materials, again, likely due to the wires. So for the series circuit seen up here on the top right, is part of one we constructed. It consists of 2 batteries and 2 resistors in series. The predicted current using Ohm's law, which was shown before, V equals IR, is 0.0204 amps, and the measured current using the ammeter was 0.02 amps, which was the last decimal place which the ammeter showed, so it could have been closer to our predicted, but it is not possible to know. And the sign flips when the direction of the current measurement is flipped. And this was consistent with conservation of charge. So then for our further calculations, we know that the sum of potential differences will be 0, and our expected values using Ohm's law are shown below: 3 volts for the battery, 0 for the wires, and the corresponding calculated values for the 2 resistors with their resistances. And then our measured values were relatively similar since our current was very similar as well, so there's only a slight difference there. And finally, our calculated resistance values using these numbers are again quite similar to what we expected based on the listed resistances of the resistors. So then for our RC circuit, the circuit consists of 2 batteries, a resistor, a bulb, and a capacitor. And the bulb was lit when we connected the circuit, but it dimmed over time due to the charging of the capacitor, which took away potential difference in current from the bulb. And so the charging and discharging times were similar within a circuit, whether the resistor was in series or not. But when the resistor was in series, the times were about 4 times as long for both charging and discharging compared to without the resistor. So using the equation I showed earlier, the natural log of the potential difference over the initial potential difference is equal to negative time over RC, which on the graph on the side, using our data we collected, we can graph this relation of the natural log component over t, which means that the slope of the graph will be equivalent to -1 over RC. And then using these numbers, we can determine that the RC value is calculated to be approximately 6 seconds. So now for the conclusion, we did do this lab in real life. So using the virtual circuit, see if you can determine how it behaved differently than the real ammeter we used. And so comparing the virtual and the real life circuits, the real ammeter has a slight internal resistance as it's not ideal. So and the battery does as well. So this means that the current is slightly smaller, which is reflected between our slight discrepancies between our predicted and measured current values shown earlier. And then again, we are doing this lab in real life. So using the ammeter to measure how long it takes to charge the capacitor and then doing it virtually, we can tell that in real life, the capacitor takes longer to charge, and this is due to the resistances and things such as the wires not being 0 as predicted, and because they are not ideal. And again, as I mentioned, our wires, some of them were kind of iffy. So this means that the capacitor would take longer to charge in real life due to this resistance. It would take longer for the current to make up for that. And that is it for my lab. Thank you.